Hi, this is Shyamala Gauri, Assistant Professor in CSE Department, Rohini College of Engineering and Technology. Subject code CGS 355 Neural Networks and Deep Learning. Unit 5 Recurrent Neural Networks. The topics covered in this presentation are autoencoders, regularized encoder. Introduction. An autoencoder is a type of neural network architecture designed for unsupervised learning, primarily used for dimensionality reduction, feature learning, and data compression. It learns to encode input data into a lower dimensional representation called the latent space or code and then decode it back to the original input. The network is trained to minimize the reconstruction error, the difference between the original input and the output generated by the decoder. Parts of autoencoder. Autoencoders are composed of two main parts. Encoder. This part of the network takes the input data and compresses it into a lower dimensional latent space representation. The encoder is typically made of one or more layers of neurons that gradually reduce the dimensionality of the input data. Decoder. The decoder takes the compressed representation from the encoder and attempts to reconstruct the original input from this representation. The decoder typically mirrors the structure of the encoder but in reverse, gradually expanding the representation back to the original data's dimensionality. Autoencoder structure. The basic structure of an autoencoder or input layer, the original data. Encoder compresses the input into a latent space representation. Latent space, a compressed encoding of the input data. Decoder reconstructs the input data from the latent space representation. Output layer, the reconstructed data ideally as close as possible to the original input. Applications of autoencoders. Dimensionality reduction. Autoencoders can be used for reducing the dimensionality of data in an unsupervised manner by taking the compressed representation from the encoder. Number two, data compression. The encoder can learn to represent data in a more compact form, which can be used for data compression. Anomaly detection. Since autoencoders learn to reconstruct the input data, they can identify anomalies by measuring the reconstruction error. If the model cannot reconstruct certain data points well, those points are flagged as anomalies. Denoising. A denoising autoencoder can be trained to learn a cleaner representation of noisy data. In this case, the autoencoder is trained to reconstruct the original input from a noisy version of the data. Regularized encoder. A regularized autoencoder refers to an autoencoder that has additional regularization terms added to the loss function to encourage certain desired properties in the learned representations. Regularization techniques help prevent the model from overfitting the training data and improve the generalization of the learned features. Autoencoders are prone to overfitting, especially when the network is large and has too many parameters relative to the available training data. Regularization helps control the capacity of the network, leading to better generalization to unseen data. It can also encourage the autoencoder to learn meaningful, sparse, or structured representations that are useful for downstream tasks. Types of regularized encoder. Number one, sparse autoencoder. The sparse autoencoder enforces sparsity in the hidden layer activations. This means that for any given input, only a small fraction of the hidden units should be active. To enforce this, a penalty term is added to the loss function based on the average activation of the hidden units. Number two, denoising autoencoder. A denoising autoencoder is a variant where the input is deliberately corrupted and the autoencoder is trained to reconstruct the original clean input. The denoising process forces the autoencoder to learn more robust and general features of the data, making it less likely to memorize noise and more likely to extract meaningful patterns. Number three, contractive autoencoder. The contractive autoencoder adds a penalty to the loss function that encourages the learned representation to be smooth and robust to small changes in the input data. This is achieved by adding a Jacobian regularization term which measures how much the activations of the hidden units change with respect to small changes in the input. Variational autoencoder. A variational autoencoder introduces a probabilistic approach to autoencoding. In VAE, the encoder outputs parameters of distribution and the latent representation is sampled from this distribution. The decoder then reconstructs the input from this latent representation, but unlike regular autoencoders, a VAE also introduces a KL divergence term in the loss function to ensure that the learned latent space distribution is close to a standard normal distribution. Thank you.